You know, modern AI can feel like total magic, right? But it's not. It's all engineering. Today, we are going to pull back the curtain on the three fundamental learning strategies that power everything from your photo app to the most advanced large language models out there. Let's get right into it. This quote just perfectly frames our entire discussion. So, answers? That's supervised learning. Patterns? That's unsupervised learning. And consequences? Well, that's reinforcement learning. These are the three core building blocks we're going to unpack, and each one has its own philosophy, its own tools, and yeah, its own challenges. All right, so let's dive into our first paradigm. This is really the foundation for today's most powerful AI systems, learning from the raw, kind of chaotic, unlabeled data of the internet. This is unsupervised learning, where the machine has to figure it all out on its own. Okay, picture this. I hand you a library with a billion books, but there's no card catalog. Unsupervised learning is basically the process of figuring out which books are about history, which are fiction, and which are poetry, just by reading them and seeing how they relate to each other. It's all about finding the structure that's already in the data without anyone telling you the right answers ahead of time. So the core goal here is actually pretty fascinating. The model isn't trying to predict some specific label. Instead, its whole job is to learn how to create a useful representation. You can think of it like a really rich numerical fingerprint for every single piece of data. And techniques like contrastive learning teach the system a super simple rule. Different versions of the same image should have very similar fingerprints, while the fingerprints of totally different images should be pushed far, far apart. Okay, so this is where the real cleverness comes in. For any given image, let's call it X, we create two slightly different or augmented versions of it, X1 and X2. That's our positive pair. The model then creates a fingerprint, that Z representation for each one. The entire job of this loss function, InfoNens in this case, is to pull those two fingerprints, Z1 and Z2, closer together, while at the same time pushing them away from the fingerprints of every other image in the batch. And by doing this millions and millions of times, the model starts to learn what features are actually fundamental to an image. Now, this approach is powerful, for sure, but it's not a silver bullet. Probably the biggest challenge is that the patterns the model learns might not actually be the ones you care about for your final task. There's also this danger of representation collapse. It's a failure mode where the model basically gets lazy and just starts outputting the exact same fingerprint for every input. And a really key difficulty is just evaluation. How do you even know if the features it learned are any good without actually testing them on some other task? Okay, so that brings us to our next paradigm. This is the classic, the one you probably first think of when you hear machine learning, supervised learning. It's kind of like studying for a test with a textbook that has all the answers in the back. With this one, the task is just crystal clear. For every input X, you have a correct output Y. An image of a cat is labeled cat. A sketchy transaction is labeled fraud. The model's whole job is just to learn the function that perfectly maps any input you give it to its correct output. It's direct, it's explicit, and it's all about making accurate predictions. And the way it learns is simply by minimizing its own error. Now, this formula, empirical risk minimization, might look a little scary, but let's just break it down. All we're trying to do is find the model parameters, that's theta, that make the average loss as small as possible across all of our training examples. So the model makes a guess, we compare that guess to the true label using a loss function L, and then we just tweak theta to make that average error smaller. It's just a fancy mathematical way of saying learn from your mistakes. This little piece of code right here shows that whole process in action. We're just looping through our data, which comes in these nice input-output pairs, X and Y. The model makes its prediction, Y_hat. The cross-entropy function calculates exactly how wrong that prediction was, and then loss.backward. That's the magic that kicks off backpropagation, the algorithm that figures out precisely how to adjust all the model's internal knobs and dials to do just a little bit better next time. It's a really tight, immediate feedback loop. And here's the catch. This paradigm's greatest strength is also its biggest weakness. It works incredibly well, but only if you have a massive, high-quality, hand-labeled data set. And creating that can be just astronomically expensive. Models can also learn to cheat by picking up on weird correlations in the data, and they often really struggle with what's called domain shift. That's when you show it new data that looks even a little bit different from what it trained on. All right, that brings us to our third and final paradigm. Now, this isn't about right or wrong answers, and it's not about finding patterns. This is about an agent learning to make a sequence of good decisions over time to achieve some long-term goal. This is all about learning from consequences.
This is the world of game playing, of robotics, of complex control systems. You've got an agent that exists inside an environment. The agent takes actions, and the environment responds with a new state, and, every once in a while, a reward. And here's the real kicker. The feedback is often super delayed. They call this the credit assignment problem. I mean, how do you know if one single move in a chess game was good until maybe 20 moves later when you see how things are playing out?
So how in the world does an agent learn to think ahead? Well, that's what this Q learning formula is all about. It basically teaches the agent to value an action based on two things: the immediate reward R it gets right away, plus the best possible future reward it could get from whatever state it lands in next. That little gamma factor discounts future rewards, so the agent has to balance short-term gains with long-term opportunities. And this code, this is basically the agent's entire life in a nutshell. It's just a continuous loop of trial and error. For each episode, it starts in some state, S, it picks an action, A, often using a strategy like epsilon greedy to balance doing what it knows works with exploring new things. It tries that action, sees what happens, the new state S2 and the reward R, and then uses that experience to update its strategy. Lather, rinse, and repeat, maybe 1 billion times. RL is incredibly powerful, but man, it is notoriously difficult to get right. It's what we call sample inefficient. It can take millions, sometimes billions of interactions to learn anything useful. Training can be really unstable, and one of the absolute hardest parts is reward engineering, trying to design a reward that actually encourages the behavior you want without creating some crazy unintended loophole. And of course, deploying an agent that learns by trial and error in the real world, well, that raises massive safety concerns. Okay, so we've got these 3 totally different ways of learning, right? But the real magic of modern AI, especially large language models, isn't in just using one of them. It's in the sophisticated, multi-stage pipeline that actually combines all 3. And this pipeline, it is just a masterclass in how to combine them. First, step 1 is self-supervised learning on a planetary scale, just absorbing grammar, facts, and reasoning from the raw text of the internet. Then, step 2 is supervised fine-tuning, where it's explicitly taught a specific skill, like how to be a helpful chatbot, using high-quality examples of questions and answers. And finally, step 3 uses reinforcement learning to align its behavior, to steer it away from being harmful or unhelpful. Each paradigm plays a very specific, absolutely critical role. So, we've seen what they are, we've seen how they get combined, but how do you actually decide where to start for your own problem? Let's try to frame this as a practical guide for choosing the right tool for the job. This really is the fundamental question every single person in machine learning has to ask. And the answer isn't about which one is best in some abstract sense. It's about which one is best suited to the real-world constraints of your problem. It almost always comes down to the nature of your data, the type of feedback you can get, and the ultimate goal you're trying to achieve. This table pretty much breaks it all down. Let's look. If you have clean, labeled data and a clear prediction target, supervised learning is your go-to. Easy. If you have tons of data but no labels, or you need to learn some general-purpose features for other tasks, you're going to start with unsupervised learning. And finally, if your problem is all about making a sequence of decisions to optimize some long-term outcome, well, you need the power of reinforcement learning. The data you have and the feedback you can get almost always point you in the right direction. So, at the end of the day, even though we've spent all this time breaking them down into 3 separate boxes, the future of AI is clearly hybrid. The most powerful systems don't try to force a problem into just one box. They leverage the unique strengths of each paradigm, using unsupervised learning to build a vast foundation of world knowledge, then using supervised learning to teach specific skills, and finally using reinforcement learning to align the final result with our human values. The real mastery isn't in choosing just one, but in knowing how to weave them all together.